I would like to begin by thanking sincerely you for the invitation and for the opportunity to celebrate this wonderful anniversary with you. And for this occasion, I would like to give you some gift. This is whiskey, 15 years old as your company, and congratulate beautiful company.
Oh, thank you. What is the most expensive whiskey then? Shall we wait with our company any longer for more present like this? Thank you. It's a surprise to me. Thank you very much.
Congratulated one time. Okay, so I will try to keep my speech as short as possible because I think everyone is already waiting for the banquet. Okay, at the beginning, I would like to say what kind of person Zbyszek is. When I try to find best way to describe him, I find it necessary to refer to job offer posted on Instytut Fotonowy webpage. Nevertheless, I always very worried, very interested why Instytut Fotonowy is in English. Why only Polish version of your company is?
For the jobs description, you mean?
No. You're on the web page. When you open the English version of your company,
there's no job announcements. That's true.
No. There is Instytut Fotonowy. There is not Photonic Institute or something like this. The name is still in Polish.
I like the name. I just like the name.
Okay. So, nevertheless, please look at this. Please look at this job offer. So, first of all, I think first thing that comes to my mind when I try to describe Zbyszek is he's extremely smart. He can build a spacecraft. The second thing is that he is worried about details, always details, because he plans to hire painters to have best interior decoration on his spacecrafts. And the third thing, and it is most funny, that he is a great supporter of a tax office employees, because this is only people from the tax office are accepted without a test period. Okay,
yeah,
so
you need to be mean.
according to above, I think we can say for sure that he has a sense of humor. Okay, after this short introduction, it's time to say how it all started. When I was preparing this presentation, I checked when I met Zbyszek for the first time. And it was a kind of surprise for me that I met him on 21st of March 2014. On that day, there is a funny tradition. It's a day of truancy in Poland. So a day from school. One of the most spectacular thing I should say about Zbyszek is that he made truancy from the university and he never come back. So I have known Zbyszek for almost 9 years, and all mentioned years I perceived time spent with Zbyszek as a great adventure. I have to emphasize one thing. Zbyszek recommended me Ayn Rand book, this Atlas Shrugged. And on every page, Ayn Rand exposes the hypocrisy of the system that parasitizes of society. According to Zbyszek, for certain, he can be perceived as a hypocrite. Okay, so on this slide you can see ordinary solar simulator. And what Zbyszek done with this? He set up this solar simulator and horizontally. So in this way, Zbyszek introduced us our first device, which was produced by Instytut Fotonowy, and this is photoelectric spectrometer, which has a light bulb in horizontally position, lying down configuration. And again, I would like to remind you that the date when I first came across his email, it was a truancy day, wasn't it? Okay. So it was the funny beginning, so now we go further. One of the great challenges of our fancy society today is the generation of clean energy. Energy that will allow us to continue to develop and create new things. One source of energy is the sun, and we can use its energy in many known ways, either through photocatalysis or artificial photosynthesis, or we can use as in photoelectrochemistry, what photoelectrochemistry cells, and we can make oxidation or photoreduction, and we can produce different chemical compounds. But in each of these roads, that is very important to convert solar energy as efficiently and selectively as possible. One of the example of photoelectrochemical reaction is photoelectrochemical reduction of carbon dioxide using solar energy, and this it's a chemical process. We can reduce carbon dioxide to carbon monoxide or different fuels, almost to alcohols, but nevertheless, in all photoelectrochemical processes, we all usually use two compartment device, which one we have working electrode, photoanode or photocathode, and it's divided by membrane to not to allow to mix the products. And this is what I mean, what I say solar energy. General, we need energy above 1.5 electronvolts, so this is almost half of the sun energy which go to the Earth's surface, so there is a lot of energy we can use in our experiments. At the heart of every photoelectrochemical cell, there is a semiconductors. In order to efficiently utilize solar energy, it is important to synthesize nanocrystals with a very good defined structures, boundary, high crystallinity, and also as porous system. Okay, so now I go to the first part of my topic. And when a photon falls to a surface of a semiconductor, it generates an electron and hole pair. Depending on the properties of the semiconductor and the environment in which it's placed, either a hole or an electron migrates to the surface. I would like first to look at the situation from the point of view of the migration to the surface of the holes, so I will focus on the oxidation, photooxidation process. It's very difficult to show this data to you after these talks before, but nevertheless, this is kind of a very traditional point of view, and I hope we can discuss later about what is good or not. But I asked Zbyszek to explain this quasi-Fermi level for me during this Q&A session, so he can tell more about these quasi-Fermi levels, because I don't completely understand what does it mean. Okay, it will be tomorrow or the day after tomorrow. Okay, so nevertheless, when the photon goes to the, it's absorbed by a semiconductor, it can generate hole and electron, and if we have lucky and the depletion layer is enough big and we have electric field which allow go to the hole to the surface, we can have a photooxidation process at the surface. It can be recombine, electron and hole can recombine in the bulk of the semiconductor. Also, it recombine hole on the defects of the structure on the surface, and nevertheless there is a problem because sometimes holes and electron can react with the semiconductor. But finally, if this all things not happened, we can have oxidation process at the surface of the semiconductor. So the surface structure of the semiconductor is very important. When we increase its crystallinity as well as we increase the pore size, we influence the kinetics of the photooxidation reaction. So this is tungsten trioxide heated in 550 Celsius degree, and we heat it more to 100 Celsius degree temperature. So when we look at the photocurrent response, we can see that the kinetic of the creation of the photocurrent is much more faster when we have much more crystalline structures. Okay, ladies and gentlemen, what is the most important thing in our life? Yes, but this is very important thing. In my opinion, the most important thing is time. So we want to stop it down or slow it down, or we can become immortal. Yes?
Perhaps, yeah, why not?
Yes, this is the second thing which is very connected with Zbyszek, immortality, but only statistical. Okay, the time course of the process during the photooxidation of water is shown on this figure, and the most fastest is the electron hole formation, and the most time consuming is the fusion in electrolyte. So the most important thing during the photooxidation is the concentration of holes, lifetime holes at the surface. Also, it is possible to multi-electron reaction and charge separation. In this very interesting paper, not this one, it should be different paper, this is 2020, okay, this is my mistake, but there is very interesting paper with this picture. This is Gretzel-Durand paper, how we can oxidize water on the surface of the semiconductor with oxygen. So they prove that on this type of semiconductors, there is process needs 4 holes, but in the same time and space. So when we want to oxidize water, we should have on the same time and place 4 holes on the surface on this semiconductor. So to take this, when we want this process, we need really slow down the fusion of the holes and the recombination of the holes. Okay, so in our laboratory, we try to work with polyoxometallites, and these structures are commonly known. There is long-established substances that catalyze chemical reaction as well as stabilize charge due to their structure. And proving the applicability of these materials in water photooxidation reaction was one of our objectives. We proved this effect a few years ago, but nevertheless, we don't know what is the mechanism behind this photooxidation process. And I want to show you our new results, how we try to find what happened on the semiconductor covered by these polyoxometallites. So we try to use, we use transient absorption spectroscopy, and it is possible to track lifetime of the generated carriers. The absorption decay spectra are mainly influenced by 3 recombination process. So first one is recombination hole electron. The second one, this is the recombination on the surface states, on the traps and the defects of the structure of the semiconductor. This is electron hole recombination, and this is other process connected to the recombination of the carriers. And through the use of the scavengers, we can identify absorption region for electron and holes. So region which is, so when we have transient absorption spectra, we on this region we can say this is the region when holes are absorption of the spectra, and for this 700 nanometers, there is a region where electron absorb spectra, and this is 2D case of the holes, the red one, and the black one, this is electrons. And this is our results. We will consider the impact of 3 different pumps. The first one was Kegging type polyoxometallites. The first one is with tungsten as a heteroatom, and the second one with molybdenum heteroatom. And the last polyoxometalite is kind of the first and the second one was a very spherical, it was spherical structure, and the third one, it is Dawson type polyoxometalite, which is ellipsoid with ellipsoid shape and with a tungsten heteroatom inside. And the idea of this experiment was to test the influence of polyoxometalite on the oxidation process. So how it looks like our experiment. So we measured the time decay for our materials in pure acid, polyoxometalate, in pure acid, this is methanesulfonic acid. And secondly, we put polyoxometalite inside the solution. We measured the time decay of the create holes, and after this we take off the electrode, we wash it with acid, and we put to the electrolyte one more this electrode, and we measure one more time decays. And all pumps when it was present in the electrolyte increase second time constant, and this is for all this polyoxometalite the same situation. But when we compare situation after removing the polyoxometalites from the electrolyte, we can notice very interesting thing, because Dawson type polyoxometalite still increase second time constant. So it means that we have still changing in depletion region of this unspherical polyoxometalite. So we think that this polyoxometalite works as a plasmonic structure and cause an evanescent electric field. This is the second very interesting observation. We use Kelvin probe measurement to see how it looks like work function of the level of the work function of our system after the modification of the structure. And for Dawson type polyoxometalite, the work function was have the lowest value. And there is also very interesting thing connected with Zbyszek, because I have spent a lot of time discussing with Zbyszek the measurement on this quantity on Kelvin probe measurements, and sometimes I have impression that it is much more easier to catch healthy fish in Odra River than make proper Kelvin probe measurements.
That's perhaps true, yes.
Yes, but I know Joanna will show tomorrow how it works proper.
Yes. I don't know if we can, what does it mean proper actually in this context?
We can ask Zbyszek.
I will be giving talk about that tomorrow.
Okay, so in conclusion, I can say with a clear consistency that nature does not play fair. And explaining the effect of pumps on water oxidation is much more complicated than we thought when we started working with them. So we have defined at least 4 main directions for the influence of polyoxometalates on photooxidation. The first one, this is trapping of water molecules in the polyoxometalite cages. Second one, there is charge stabilization in this polyoxometallate structure. And the new one, there is adsorption of the surface and influence on the depletion region of the semiconductor. Also, polyoxometallates changing the position of the Fermi level. After this very simple water oxidation reaction, I would like to introduce you to new protagonist in my story, and this is the photoreduction process. And I will omit hydrogen generation, and I will go to the carbon dioxide reduction. Generally, it has been reported that 1 electron reduction of carbon dioxide involves the formation of carbon radical intermediate during the first step of the reaction. However, this creation of the carbon radical needs almost -2 electron of 2 volts versus a hydrogen electron, and it's completely thermodynamically disfavored and systematically considered as the rate limiting step for the whole reaction. So we want to have carbon dioxide reduction using multi-electron system. And this multi-electron proton-assisted carbon dioxide photoreduction is another studied mechanism, as it presents much more favorable redox potential. However, CO2 reduction to the same product when we use multi-electron reduction may be proceed via different and competing pathways. So we have a choice. We can reduce carbon dioxide using a carbon radical, or and it will be much more selective, or more efficient but not much selective multi-electron pathways. So this is the beginning of my talk about the photoreduction. Challenges of the photoelectrochemical carbon dioxide reduction generally lies in 3 aspects: poor light absorption, inefficient charge separation, and slow surface catalytic conversion. The light absorption range is largely determined by the band gap of semiconductor materials, also by their surface properties. Even if the light absorption is good, photoexcited charge carriers sometimes are subjected to serious recombination as mediated by surface states, defects, or impurities. The transport of minority carriers towards the surface is largely dependent on the electronic structure of the interface and may become embedded when the built-in electronic field is weak. The last challenge is the surface catalytic conversion owing to the sophisticated CO2 reduction electrochemistry. CO2 contains 2 stable CO bonds that are difficult to activate and dissociate. As a result, photoelectrochemical carbon dioxide reduction is kinetically slow compared with the competing hydrogen evolution reaction, and usually requires large overpotential. Moreover, carbon dioxide reduction has several possible reaction pathways and hence poor reaction selectivity. Proper co-catalysts are often introduced to improve the activity and selectivity of the surface. A robust physical contact between the semiconductor and co-catalyst is also of critical problem of connection between this semiconductor and co-catalyst. And this is what we started from the carbon dioxide photoreduction. When we want to create carbon radical and we use only 1 electron or 1 hole, one carrier, it's fast process and the time is not very important. But when we want to create C2 products or more, our system needs much more electrons, and also the recombination time of electron and holes we should be much more longer in case of 1 electron process. So the common trace for carbon-2 product is the multiple electron coupled to proton transfer reaction and CC coupling. And our crucial enemies, there is electron hole recombination and the limiting that this process should be, the process of the reduction should be in short time and the same place, so the same location. And the research goal of our laboratory is the efficient conversion of solar energy. The use of reduced graphene oxide has become interesting challenge. In our research, we used reduced graphene oxide layers in form of flakes that form a continuous layer on the electrode surface. And this is the IFM picture of highly oriented pyrolyzed graphite with with 20 layers of reduced graphene oxide and 20 layers of graphene oxide layers. And the estimate thickness of the 20 layers of reduced graphene oxide was about 10 nanometers, and the thickness difference between the graphene oxide, it's because one graphene oxide is about 3.5 angstrom, and our the thickness of our one layer is about 5 angstrom, and the difference between this thickness of these two layers is because our reduced graphene oxide have some different surface and have some oxygen groups and so on the surface. We measure the position of the, we measure work function of our system, our modification with reduced graphene oxide, and we also heat our materials in different temperature. And our deposit of reduced graphene oxide was deposited on FTO, so this is conductive glove support. Manipulating the number of RGO layers directly affects the Fermi level position, mainly because it induces charge transfer between the substrate and RGO. The charges are subsequently distributed through the layer. However, the electrode thickness affects other key properties of the material, such as thermal electrical conductivity and transparency. Our measurements clarify that increasing the number of RGO layer drives the Fermi level towards more negative, and the observed shift in the Fermi level position can be attributed to two phenomena. The first phenomenon is rooted in the GO and RGO synthesis. As the graphene oxide is heated, functional groups are eliminated and the electrical conductivity increases. So to conclude this slide, we can make the position of RGO layer with very specific work function, and we combine these results with our system. So we synthesize copper oxide. Okay, I don't know, you see, okay. It is nanoneedles here, but I don't see it very clearly. Okay, nevertheless, we synthesize copper-1, copper-2 oxide system. We deposit on this system RGO, and we, on this mixed system, so copper oxide, copper-1 oxide, and copper-2 oxide, we put RGO, and after this we put hexagonal tungsten trioxide. And after this, we put another one layer of reduced graphene oxide. So, because we know the Fermi level position of this system, we know position work function of hexagonal tungsten trioxide, we can use specific layers of reduced graphene oxide to have the best position of the Fermi level of all these materials. And so finally, I would like to show you some photoelectrochemical results. The advantages of RGO were observed in the hybrid photocathode for CO2 reduction. We selected a sandwich architecture for this application. By optimizing the RGO thickness and combining the nanostructure properties of materials with the unique matching between copper-1, copper-2 oxide and hexagonal tungsten trioxide, we eliminated the surface recombination currents. So our final electrode, which is the black one, has the smallest recombination photocurrents instead of a pure system, which is a copper-copper oxide and copper-1, copper-2 oxide only with a reduced graphene oxide. Moreover, the charge transfer resistance on the working electrolyte interface was significantly reduced in the copper-1, copper-2 in our final system, and significantly increase in efficiency of the energy conversion, and the photocurrents for this final electrode was the highest photocurrents. Okay, the transient current here measurement strongly depends on the mid and upper layers of RGO. The photocurrent plateau was reached only in the full architecture containing both the mid and upper RGO layer. When RGO layer was absent, the photocurrent transients rapidly reduced to the dark current after 500 nanometers, and we see that there is a very big problem with our electrode. And now we want to see the distribution of the products, and still there is very tricky thing with optimize the system to see the products. Also, with this system, we have problem with the electron react with the electrode and we have a very big problem with the electrode. But nevertheless, this system works the best in our case. Okay, so ladies and gentlemen, one of the least appreciated skills of a good chemist is the ability to create art. Nevertheless, I am pleased to present you with a nice picture showing a schema of the system I will present. And we have traces of methanol after reducing carbon dioxide on this system, but efficiency is quite nice, but the lifetime of the system is not very long. And the very end of my presentation, I would like to mention just one more often overlooked element of photoelectrochemical cell. So this is electrolyte. First of all, I would like to draw your attention to the area at the electrolyte where due the semiconductor electrolyte interaction. The electrolyte particles are very strongly bound to the electrolyte, and diffusion is considerably restricted in this region where the electrolyte is the closest of the electrode surface. Another aspect is the size of the ions and their interactions. One technique that allows a better look at the properties of the double layer is electrochemical impedance spectroscopy. But this is a story for another time and in another place, because Zbyszek is here and he hates impedance spectroscopy.
I just know it.
Okay, so photoelectrochemical testing is remarkably simple. All you need is the sun and some kind of device, for example, multimeter for measurements. Of course, if we have a photoelectric spectrometer, we can even start trying to understand what is going on. The next step is try to understand what is happening in our semiconductor, how electron and hole interact, how the junction is formed, And the Kelvin probe is the ideal tool here. If we want to study the interface between semiconductor and electrolyte, it is good to be able to do electrochemical impedance spectroscopy. And at the very end, it is important to understand the reaction mechanism. And here, time-resolved techniques are already necessary. Photoluminescence or transient absorption spectroscopy or others. But the most important thing is to use apparatus consciously and to discuss all the time, because nature is very perverse. Okay, I would like to acknowledge people who were contributed to this work, and especially my boss Renata Solarska. And thank you very much for your attention, and I would like to end my presentation with a phrase that Zbyszek used to end his emails: cheers. And if you have any question, I would be very happy to answer them. Thank you very much.
I may have a comment if you let me, because it is not that we have problem with impedance spectroscopy, it is just doesn't satisfy our needs, and we have very particular need. We wanna use it as a cheap tool for biosensors, to do cheap diagnostics of health conditions of people. And in there, you simply cannot make too much systematic errors at the very beginning of your endeavor, because usually you are faced with just small traces of the substance you are after in an environment that is not friendly, because it is clotted with other proteins or things like that. And again, such measurement can be done in laboratory, but it is inaccessible to people, and it is very expensive. So it is, in general, it is possible in principle, but in practice, you cannot rely on that. So this is why we've got interest in impedance cameras, and why we built our own device to conquer that part. And this is why I'm biased toward against linear systems, and because it is not what we are observing in our research. So just that comment. But impedance spectroscopy is a great tool and works in so many areas. So this is it's okay.
Thank you, Zbyszek. Yes?
Krzysztof, could you comment something on the efficiencies of these systems you have shown us CO management?
If we talk about the currents, it's quite efficiently. But if we talk about the products, there is a problem, because the current is not so big, and our system not allow us to detect all the products. Also, we see that there is destroying of the electrode. So in this case, the efficiency is so the Faradaic efficiency is about 10% or less. If we have a good day or something like this. You know the system, so your question is very tricky.
No, I'm really curious. I think behind it. Yeah. We have, of course, problems with reduction of CO2, which is very demanding. So I'm just curious, maybe you have some better ideas.
Okay. The most problematic with this
product.
Yes, we detect products, but the problem is when we make the 3 or 4 or 5 hour reduction process, we see after this reduction process we have FTO surface, and this is the problem, because after all we don't know if we have reduction only by our by semiconductor or also by FTO. If we make the 1 hour reduction process, it's not possible to see the products. And this is the reason I work with Paweł, and we check much more bigger surface. And if we have bigger surface, maybe we'll much more easier to detect the products. Yes?
So like when you measure this carbon dioxide reduction and also hydrogen elution test, are you also using this photoelectric spectrometer to measuring this? Because we have this indigenous lab, and we're trying to like plan something like maybe adding some parts to the instrument to measure this carbon dioxide reduction and hydrogen elution. So what like instrument you use for this to test?
Okay, so this photoelectric spectrometer allow us to measure, because this is solar simulator, so we can use as a solar simulator. Also, we can use it as a monochromator, so we can measure the IPCE. But the most important thing when we measure the product, so how much we have hydrogen or products from the CO2 reduction, we need a good cell. And till now, Zbyszek don't have in Instytut Fotonowy good cells, which is which allow us to take inside the cell the product. We use different quartz cells, and also we can talk with Paweł about good cells.
Perhaps you can talk to Redox me that is presenting those cells. Oh, here's Jake.
Oh, great! I would like to talk with you about.
So many cells on the exhibition here. So take notice here that perhaps you can help.
And also, you need gas chromatography to detect the products.
So like when are you connecting this gas chromatograph to this machine, or just you taking the products like carbon-based fuels to in or out?
When we measure the products, we have a different place and different solar simulator. But because it is connected with the gas chromatography, which is big device, and so it is in a different place. Yes, of course, we want to have 2 or more devices from Zbyszek, but
More questions, perhaps? Okay, let's thank our speaker again.
thank you very much.